Now, a second goal that we care about is replay attacks and integrity. Remember that a replay attack happens if someone writes down a message and then resends it. And if the replay attack works and the scheme is vulnerable, then someone might be tricked into thinking the message was sent twice, even though it was only sent once. So there's actually two types of replay attacks we should look at and make sure we defend against both. One type is a replay attack between two different connections, where I write down something from a previous connection and then resend it in the current connection. And the other type of replay attack is resending messages from the same connection. So we'll look at both of them and make sure we stop both types of replay attacks. So here, we're thinking about the replay attack where somebody writes down an encrypted message from an old TLS connection and then replays that message in the current TLS connection. How do we make sure that messages cannot be replayed across different connections? Well, remember that these two messages at the beginning exchange random numbers, and then the symmetric keys that you use to encrypt and MAC messages use a key derived from those random numbers. So in other words, every handshake uses different random numbers. Therefore, every handshake derives different symmetric keys. So if you take a message from a previous connection and try to replay it in the current connection, the keys used in the two connections are different, so the message will not be accepted. The MAC won't check out. So this is how you stop replay attacks across different connections. But how do you stop replay attacks from the same connection? What if someone takes this message, writes it down, they don't decrypt it or modify it, they just write down the raw sequence of bits, and then they try to replay that sequence of bits later in the same connection? Well, now, in the same connection, we're still using the same keys, so this previous defense didn't quite work. So we'll add one more thing just to make sure that people cannot replay attack inside of the current connection. And what we'll do is we'll add something called a record number in the TLS payload. This is something new. We haven't previously seen it. But you can think of a record number like a timestamp. And what we've done is in the encryption, we will write down what time the message was sent, or we'll use some sort of counter that is uniquely increasing. And what this does is it defends against replay attacks. If someone takes an old message, writes it down, and then tries to replay it later, the timestamp will be the same, or the counter will be the same, and this will tell the recipient that these are actually the same message replayed twice. It's not two different messages. If the attacker wanted to replay messages, the record number or the timestamp would be the same, and the server knows that it's the same message duplicated. If the client really wanted to send the same thing twice, then those two messages would have different timestamps, and that's how the server knows that they are actually two different messages. So this is how you stop replay attacks inside the same connection. Now, one thing that people sometimes get confused about is the difference between TLS record numbers and TCP sequence numbers. It seems like both of these help us tag messages with counters or timestamps, but they're doing two different things at two different layers. So TCP sequence numbers, they work at layer 4, where there is no encryption, and they're just used to help us reassemble messages. So TCP sequence numbers are not encrypted. They're in the outer layer 4 header. Remember, we wrap headers around each other. TCP is in the outer header. Anybody can modify those. A man in the middle could modify those. And TCP doesn't stop that. It's just for reassembling packets into the correct order. By contrast, record numbers live inside the TLS payload. So they live inside the encryption. And when you send that record number or timestamp, you have to encrypt it. And this way, an attacker cannot modify the record number to make it look like the replayed message was actually two different messages. So they might look similar at first, but these two numbers serve different purposes at different layers.